All right, so now that we have the helper function available, we are in a position to start writing the code for binary search to find the minimum shipping capacity that we need to, let's say, fulfill a given order. So let's start writing a function called, say, binary search, shipping, just a name. So the idea is that, well, look, I will pass to this function weights, say and d. So the number, so the list of weights and the number of days, and I'll try to figure out the least shipping capacity with which this order can be fulfilled. So like I said, just put a comment here: use binary search to find the minimum value, say minimum shipping capacity to ship the weights in d days. I think we should write in at most d days, right? So within d days. All right. Now, as always, binary search, we work with two pointers, a low and the high. So I just set low to 0. I set high to, let's say, len of weights times 10. Now, this is actually somewhat interesting. In fact, we discussed this before. The low value is really has to be the minimum of all this, because the shipping capacity has to be more than each of those items, right? So, really we can set low to the minimum of this, but the reason I'm putting it 0 is because I don't want to do an operation here to figure out, let's say, what is the minimum, because that is, I think binary search should find that, right? Likewise, basically, I'm putting a large value here. So instead of, if you think this is odd, we can just put a number, let's say maybe something like maybe 500, right? Because remember, the binary search is going to basically find this entire range in logarithmic time. So, in 9 or 10 iterations, we can solve this, right? So even though this number is, let's say, very, very large, right? So the idea is I just put kind of two extremes and let the search take over. I will use another, let's say, um, variable here called result. We'll talk about this later. Now, the regular binary search loop, in fact, we can just work with these two pointers. Quite interesting. So I just go and say while low is less than equal to high. Remember, this loop will terminate the moment there's an inversion, because this is low less than equal to high. The moment low becomes greater than high, the loop terminates. As always, I just go and say, well, mid is low plus high, floor division 2, because I'm kind of hitting at the middle. Remember, the search always happens at the mid location. So I ask the search here is essentially, well, if can be shipped, what are we looking at? If can be shipped, let's say, given this weights, um, given the shipping capacity that we are looking at, and let's say D being the number of days. So if this can be done, then I know that this is a feasible solution. I will hold this in the result. Right now, this is somewhat interesting, somewhat different from what we have done before. Basically, we're saying that, look, this result is feasible. However, I will not abort the search here, because remember, I am looking for the minimum capacity that does the job, right? So it may be possible that, like, for example, in this case, right, I've set high to a very large value, so which means I'm going to search at, let's say, 250 in this case. Of course, 250 can meet the requirement, right? The answer is going to be true from here, right? I mean, for the weights that I have. However, that's not the value we are looking for. In fact, we want the minimum value. So while we store this here, we still go and move the high pointer to mid -1. So the question is like, is there another value which is smaller than the present mid that can do the job, right? So that's why I continue with this result, continue with the, let's say, search. However, I do store every mid that meets the value. If, let's say, this doesn't happen, if I find that, let's say, so not can be shipped. So basically, can be shipped is like, let's say, so mid and D. So if I find that this shipment cannot be done, then I know that, look, I need to search higher. So I just go and say low is mid +1. And in fact, that's the only two conditions that we have to worry about. The interesting bit is that I will return from this the result. Now, this is quite interesting. Notice when I return the result, basically I'm going to find out the least value, because notice I keep pushing the high back. The moment I meet something, I keep pushing the high back. I'll get that result, which is the lowest value at which the shipping could be met. And that's exactly what I was after. So this binary search is a little bit different, but quite concise, quite nicely done, right? So just to sort of understand this, As always, we will put three prints so that it helps us understand what's going on. So let's say low. Um, so I put these prints low, mid, and high, and I think that should be it. Now we will see this working by looking at a binary search example on this list of weights with, let's say, 3 days as my requirement. Before running this, however, I have commented out these prints in the can be shipped function. Otherwise, the screen gets too cluttered, hard to understand, right? So basically, I'm just looking at, let's say, binary search of this. I do want to see how the pointers are moving because that is insightful. So notice I start this. Previously, I'm setting low to 0, high to 100, high to 500, and hence the mid value is 250. So I do a search at 250. Clearly, I meet the requirement. That's why I make my high to 249 because remember, the lowest capacity must be lower than this, right? So I set my high to 249. Then mid is 124. So I search at 24. I go to 123. I search at 61. All of this meets. I go to 30. I go to 14. Still meets. I go to mid of 6 and I find that look, now it's not feasible because clearly 6 cannot be the capacity, right? I mean, I can't transfer this item, for example, with 6 units. So I say, okay, let's try to search bigger. So I go to, for example, low of 7, mid becomes 10. I find that at 10, I do meet this, and we will verify this a little bit later. So my high becomes 9 because 10 minus 1. My mid is 8. So I search at 8. At 8, I cannot meet this. So I say, okay, let's increase my low to 9. And the moment that I do this, I do meet this. My result, remember, is always tracking the lowest value where I'm meeting this. I increase my mid value. So I do meet this. I increase my low value. Low becomes 10, more than 9, and hence the loop terminates. Very, very interesting. Let's just verify this. So basically, the answer here is 9. Now, if I were to use my can be shipped function, let's say for 8, I should see a false. In fact, it returns a false. If I try with, let's say, 9, it should be true, right? So exactly what we're looking at. Like I said, I've disabled those prints, but if you want, you can turn them on again to kind of get a better understanding, right? Let's just try to make this list, let's say, a little bit larger, say 23, 1, 18, 19, 27, let's say. Obviously these items are large. So let's say I try maybe 30, right? So can I ship all this in 30 days? In 3 days with a ship of capacity 30? Answer is false. In fact, we can now run a binary search to find out what is the minimum capacity to, let's say, do this, right? So when I take this list, copy it here. Now this list could be long, it doesn't really matter. Yeah, when I run this if I were to do this in 3 days, I run my binary search. In fact, it tells me the minimum capacity is 46. Quite hard to tell immediately, but look how binary search finds it. Search the 250, 124, 61, 30. 30, since we know the answer is 46, 30 doesn't cut it. I mean, 30 is not feasible. So I start increasing the low. I search at 45. I make low 46. Mid is 53. So then again, I start coming down. Notice, the way the search is working, I'm not stopping at the first value that's found feasible. I keep coming down till they all become equal. At this point, I just meet it, and indeed, low becomes more than high, and the loop terminates. Very, very beautiful. So that's 46. Now we can verify this here. If I were to try, let's say 45 for my answer, it tells me false. 46 should give me true. In fact, we will, add some prints to 46 is indeed true. Let's just restore these prints back to see how 46, let's say, does it, right? So if I were to, let's say, do this, so we know that 46 does the job, but let's see how it does it, right? So if I were to now run this, it tells me, okay, I'll do this in 3 days. Basically, the first day will be 5 plus 2, 7 plus 7, 14, 11, 12, 16, 28 kgs to 28 units. Next, I have 42 units. And next, in fact, I have 46 units. Amazing. So these 3 days, I get the job done, right? Now, let's say the same problem was, asked for, let's say, 4 days, right? So clearly 46 can do it in 3 days. 46 can also do it in 4 days. But then we can run binary search, and one would think that the capacity would come down, right? And it should, because we have more time to, let's say, do this. Now, remember, I had all those prints being printed. So my min cap is being printed at the very end. It's 37 days now. So I can, in fact, achieve this thing in 37 days. Really, really interesting if you think about it. I'm sorry, I can achieve this with a capacity of 37 this should be true, and indeed it is true, and this is the distribution, right? Quite hard, when you first think about it, but see how binary search is helping us, because we were able to split the zone between infeasible and feasible, and then a binary search, very, very concise function, does the job for us. Now, of course, you can remove those prints once you're clear with them, but do think about how this is working, how the loop is actually running, how does it terminate. Very interesting. As always, on our website www.ybyte.in, we have lots and lots of contents for you to learn programming, for you to learn algorithms. Do look at it and enjoy programming. Take care. Thank you so much. Bye bye.